Okay, I think we can get started. Welcome everyone to today's CNCF webinar. The topic is Zero Trust Security for Cloud Native Apps. I'm Sanjeev Rampal. I'm a principal engineer in the Container Platform Engineering team at Cisco. Thanks to all of you who are joining us. Today's topic is at the intersection of two very, very important areas, security and cloud native technologies. So this should be super interesting, and I'm really looking forward to this presentation. Our presenters today are Chaim Hellman, who is the co-founder and CTO at Octarine, and Yevgeny Pats, who is the head of security at Octarine. A couple of housekeeping items. During the webinar, you will not be able to talk as an attendee, but there is a QA box, so feel free to drop your questions in there, and we'll get to as many as we can at the end. The session is being recorded, and links will be sent out afterwards, along with the link to the slides. With that, I'm going to hand it over to Chaim and Evgeny. Please introduce yourselves and go ahead with the presentation.
Hello, everyone. I'm Chaim from Octarine. I'm the CTO and co-founder of Octarine. And the topic of today is security for cloud native application. Thanks, Sanjeev, for the intro. And as you said, it's an intersection of two very, very significant topics. One is very fundamental and pretty old and has been there for a long time, the topic of security, along with the new technologies around cloud native infrastructure and applications. So when we're talking about cloud native applications, we're talking about not just a shift or a fundamental shift in the way applications are architected, broken down into microservices, but also in how both compute and network are virtualized. And that shift and that change has to translate to the tools that we use to secure those environments. This talk, I'm going to go over what drives this shift and what are the necessary requirements of a new security framework for this new world. So first, let's see what's different about cloud native applications and microservices, and what's the security challenges that we can identify in this new environment. So we have this new architecture, and it breaks monolithic applications to many microservices. And the microservices, they communicate over the network, creating massive amounts of east-west traffic. In typical deployments today, more than 80% of the traffic is east-west. This traffic targets thousands of internal APIs. Each one of those APIs may be a target of an attack looking to access data or perform lateral movement. To monitor this traffic and secure those APIs, you have to have a solution that is as scalable as those cloud-native workloads. So we'll talk more later about what it takes for a solution to be scalable. So if cloud-native means high volume, it also means high velocity. Businesses, they adopt the cloud-native approach because they want to be agile. So cloud-native applications are usually coupled with agile deployment model. What that means is that new services and new versions of those services are deployed frequently, in some cases, several times a day. And they're deployed in a decentralized way. So each team, and in some cases, each developer, is responsible for deploying parts of an application. Keeping track of what's deployed and how it behaves is fundamental to effective security. So the days of security team using spreadsheets to track assets and dependencies are gone, or at least they should be. If you can't see what pieces of software are running in your data center, or if you don't understand how they behave, there's no way for you to know how secure are you, and there's no way to detect any attacks or anything unusual in your environment when it actually happens in real time. If you look at the existing arsenal of security tools, they're mostly focused, they rely on the five tuple: the initiator IP and port, the target IP and port, and the protocol. But now we're moving to a world where instead of having few applications, which are using distinct protocols and have static, well-known network addresses, we have a world of many scale-out services that communicate using a small set of protocols, mostly HTTP, HTTPS, some message broker protocols, and where network identity is no longer coupled with a particular workload. So our services now are stateless. They can go down, go up at any given time. The orchestrator has freedom to spin up containers and allocate IP addresses to those containers. So the connection between an IP identity and a workload is gone. So just knowing that a server or something, an entity within a certain IP contacted another IP on port 8080 using HTTP, it doesn't say much about who is the initiator and what is it trying to do. Even worse, when we're talking about HTTPS, we don't have any visibility as to what are the payloads, what are the endpoints that are being accessed. We have really very little visibility as to what's actually going on. And now in this environment, we also see a lot of massive use of load balancers, proxies, reverse proxies, API gateways, especially in public clouds. And all those intermediaries, they break the relationship between the originating IP and the actual IP that we see on the network.
I'm sorry to interrupt. There was a quick question from the audience whether we should still be seeing slide 1 or are you on those?
Yeah, I'm still talking about security tools and methodology.
Thank you.
So current tools are becoming ineffective because they fail to distinguish between what's good and what's bad traffic. They're also harder to manage since the number of entities and the number of rules that are associated with those entities just keeps growing. The way we handle authentication is also problematic, since the existing methods of delivering access tokens to workloads rely on us knowing where they run and when they're deployed. The same for encryption and certificates. We still have many places where whatever access control policy is in place is managed by configuration files. These files, they become obsolete as soon as they're deployed. Moving on. So now we figured that we actually have a problem. Let's examine what are the principles that we need to adopt when we try to build a new cloud-native application security framework. So identity is obviously a fundamental component of such a solution. We need to know for certain who are the actors in our network. And since network identity won't do, we should rely on identity that is attached to the workload. And that identity is the one being transmitted and verified across the network using mechanisms like mutual TLS in layer 4 and signed JWTs in layer 7. There are several challenges around application identity. The first one is how do we determine the identity of an application, also called attestation. So one option could be based on the binary or the image. We can hash it and attach a certain hash to an identity. That creates some problems around versioning. So when we create a new version of our binary or of our container image, we'll have a different hash. So we still have to know that it's the same workload, but we do want to know that maybe it's a different version, so behavior might be different. Identity might be based on the workload identity in the orchestrator. So Kubernetes has deployment names, service names. There are all kinds of ways to identify a workload. Of course, a DNS address could be another way to identify the workload. So in Istio, we rely on the service, and the service kind of is related to the DNS name and the port that this workload exposes, rather than specifically to a deployment. And a good solution should probably have a combination of all those approaches. So we do want to look at the binaries. We do want to have integration with the orchestrator, and we do want to validate that the DNS address that the clients will be addressing is actually represents the right workload. The second problem is about delivering credentials to the workload. That's the identity bootstrapping problem. So we have workloads that are constantly being spun up. And obviously, we don't want any credentials in the code itself or the container image. And even secret management, so the native secret management capabilities of, let's say, Kubernetes have several flaws and drawbacks in terms of security, in terms of the granularity of access to those secrets. What we really want to do is to have a minimal exposure to unauthorized access or spoofing or man-in-the-middle attack. So we want the credentials to be delivered at the very last moment before the workload actually needs to use them. The third problem is how do we minimize the damage of credential theft? If a container is breached, compromised, if our secret management system has been compromised, assuming we identified it, how do we minimize the damage there? And that could be solved by a frequent rotation of credentials and a runtime binary correlation of who's actually using those credentials, as well as anomaly detection. Regarding identity, I really recommend looking at Spiffy if you haven't already. It's part of the CNCF ecosystem, and it's a great open source project dealing with supplying workloads with those kinds of verifiable identities. All right. So microservices are not developed the same way that traditional applications were. We're moving from a world where we use a uniform development platform like Java Spring to develop all our applications, to a world where we're using the best tool for each task, which means that a single application may have components written in C++, some written in Go, some written in Node.js. And obviously, you want a security solution that will cover all your workloads in a uniform way, regardless of how they were created and where they were deployed. However, if you re-implement the security libraries in each language, now you have to qualify each implementation separately. So a good solution will share not only the principles or the protocols, but the actual implementation. And that way, you only have to qualify that solution once. Obviously, you want your solution to work on public clouds and on-prem and in between those clouds. And it sounds obvious, but it's really easier said than done. When you're using a public cloud, the provider, they integrate their IAM and logging solutions into every component of their platform. Your compute, your networking, your data services, and it's only natural to manage your visibility and identity and access control with those native tools. But a good multi-cloud solution, it has to offer both hooks to integrate those native IAM and logging and auditing tools, but it needs to extend their capabilities where their capabilities missing. And it has to offer a uniform user experience. So if you want to migrate an application from your on-prem environment to the public cloud, or maybe from one public cloud to another, your experience in terms of security should stay the same. So the last part is about trust. So your traffic is going to be traveling across networks, and they will have varying trust levels. So it could be within a VPC, among VPCs, among zones, among clouds. So it's best to adopt the zero trust approach, where all your communication is encrypted and authenticated at the endpoint. That means that the initiator identifies itself and the server authenticates that identity. And of course, everything in the middle has to be encrypted. Some people think that encryption is costly, but today with modern CPUs, that overhead is actually very small, and it's actually smaller than the overhead of parsing the payload in many cases. And encryption is not just critical in protecting the actual payload from eavesdropping. It's also the only way to implement strong authentication that's not vulnerable to man-in-the-middle attack. So we talked about the problem. We talked about the design principles. Now let's look a little bit at possible implementation. So if we're going back to the principle of application independence, as the sidecar model is the way to add some capabilities in a uniform way for different kinds of applications. So the sidecar is a separate process. It's running alongside the service and extending its capabilities. In the CNCF world, I guess the most famous sidecar is Envoy, as it handles both some security aspects and many routing and failover tasks. So what would a security sidecar job, what would it be? So a security sidecar has to trap all inbound and outbound traffic to a service, and it has to enforce encryption, authentication, and authorization for that service. It also has to report traffic, log or trace traffic information to a central location where it can be analyzed and audited in the future. Obviously, all the communication between the sidecar or the proxy to any control plane, whether it's the control plane handling telemetry or the control plane providing access control rules, it has to be secure, which means it has to be encrypted and authenticated. Now, some tasks that are very complex in this dynamic environments, like key management, are greatly simplified. They're a lot easier when you have this standard component running at every endpoint. So now your sidecar is the one handling communication with your CA and rotations rotation of credentials and attestation. So what happens if we have an intruder in the network? So if it doesn't have that sidecar that has gone through the process of obtaining identity, it will not be able to authenticate itself, and obviously any attempts of accessing other services will be denied. And we'll start getting alerts that a possible intrusion is going on. And that's really the essence of zero trust, because it doesn't matter how close the intruder got to our workloads. It could be in our VPC with an IP that's in our subnet. It could be behind any of our firewalls. But since it didn't go through an authorized deployment process, it will not have identity, and it will fail authentication. So even if we have an authorized workload that does have a proxy and does have an identity, and that workload is compromised, if we have an effective access control policy in place, it will limit the blast radius of the attack to just a very small subset of the services and resources, instead of exposing all the resources that are available across the network. In addition to just creating a strict access control policy and enforcing it, again, binary validation can and should be used to make sure that the application talking to the proxy is the right application. Pattern-based detection can be used to detect API scans, SQL injection, code injection, and anomaly detection tools can be used to detect a change in the use pattern, like the payload size and the request frequency. So we started talking about access control policy. So it is quite a challenge in this high volume and high velocity to maintain an access control policy that is effective but still manageable at this scale. And so I'd like to go over a few of the best practices we think are, if you follow them, you're in the right path. So first, it's using whitelist. So it's much easier to characterize a workload by what it's supposed to do, what is the intent for that workload, rather than defining and verifying what is it, what an attack would look like. So there are endless kinds of attacks, but there is a very limited set of actions that a service should be doing. So moving from a blacklist approach to a declarative whitelist approach makes your policy a lot more manageable, and usually your set of rules much smaller. Automation is also extremely important in this scale. So you should have an automated process in place that constantly evaluates your actual access patterns, and it modifies your policy, your whitelist, to ensure that you still maintain list privilege at all times, because now you have services changing their behaviors, new services being deployed. It's very easy to give a very wide whitelist that allows everything, but that kind of defeats the purpose. So if you have a tool that kind of audits your actual traffic and translate it to real policy, then you're on the right path to having the least privilege and really a tight and relevant access policy. So the language that we use to define policy is also important. many systems, they take the RBAC approach, the role-based access control, which is very effective for setting access control to people, and they try to extend it to work for services. So in RBAC, you have to manage, in addition to principles and actions, you have to have a list of roles, and each role is a set of actions, and then you bind those roles to principles. What we found looking at actual service-to-service communication cases is that the ABAC approach, the attribute-based access control, where there are no roles and we just assign allowed actions to the attributes that the service has, we find it a lot more intuitive, and it usually leads to a simpler and more flexible set of rules. I invite you to check out Maple. It's an open source project that we've released. It includes a language, a policy definition language, an engine to interpret that language, and an Istio authorization adapter. It's an easy to use yet very powerful language for this, and it's meant specifically to define access control rules for service-to-service interactions. And now I'll yield the floor to Evgeny.
Thanks, Chaim. Hi, everyone. So as Sanjeev mentioned, I'm head of security at Octarine, and I'll show you a few basic attack scenarios in cloud-native environment, so we can a little bit understand of how some of those attack scenarios looks like, and get the feeling and understand how we can mitigate them using some of the concepts and design principles that Chaim talked. So I'll share my screen. 1 second. All right. So this is a basic cloud native architecture, which consists of the famous guestbook application, which is the Hello World of the cloud native, the Hello World app for cloud native applications, and we have also a path store, which is a basic application, a basic REST API application. So actually it consists of four services. We have a front-end app that gets all the incoming traffic from the world. We have the Redis service, which is the database. We have some sensitive service, and we have the path store, which exposes REST API. So the sensitive service actually communicate both with the database and both with the REST API, and we also have 1 second. Yeah. So just I think that my screen. Okay. Yeah, I think my screen shows fine. So yeah, sorry. So we have the front-end application that communicates with the database and with the path store as well. So I'll share my terminal. So we'll start. So here I can see all my old pods of this deployment, and so we'll start the attack from a breach pod. So in that case, we will just bash into the front end pod. Though in a real case scenario, probably the attacker will get into the front end. Pod through some remote code execution vulnerability, and probably will start from the front-end service due to the vulnerable nature of front-end application through maybe SQL injection or other logic bug, or no dependencies, or any other any other remote code execution. So now let's assume we are inside the pod already. So the first thing usually in a cloud native that an attacker will try is to try and directly talk to the Kubernetes API, because Kubernetes API actually administrates the whole Kubernetes cluster, and we can get a lot of information from there. So let's download the kubectl to the pod. Change to execute permissions. And now let's run it and try to see which other services are in that deployment. So to which other services we can reconnaissance and get more information and maybe move to more sensitive services. So let's do kubectl get services. So it doesn't work. We are forbidden. Looks like the cluster is configured correctly, and it uses RBUG, which is the best practice. So we are not lucky in that case. So now it doesn't mean we can't access the Kubernetes API, but that doesn't mean we can't communicate with other services or find them by those services by other means. So the second thing that we can try is to look at the environment variable. So if we look at the environment variable, we can see some IPs of probably interesting pods. So we can see here IPs and ports of Redis services. So let's do grep Redis, and we can see here IP and port of Redis. So let's connect to it. See if we can connect to that and get some interesting data from there. So we can use netcat. So we can use to get those tools. We can use apt if it's available in the container, but we can actually get it with wget or curl. So I already installed netcat using apt to save some time for the demo. So let's connect via netcat. Okay, so we're connected. Let's see all the keys. Here's Redis command, here's asterisk. Okay, we have some messages. So let's see what messages are inside. Get messages. So we can see all the messages. So that's just some 3 dummy messages that I put beforehand, the application. So it looks like we have full access to the database now. And we can read and write to the database. So that's one thing that we achieved. So let's see what else can we do. Let's see how we can discover more interesting services. So in the environment variable, it looks like we don't have other interesting information, but we can do network scan. Network scan to get other information, IPs and ports of other services around us. So a full nmap scan will take a lot of time. So we'll just scan the subnet of our pod and we'll hope to find something interesting. So our IP of the current pod is 1032.1.8. And we'll do nmap -f. It's the most commonly used port, also to save some time for the demo. And we'll scan our subnet 10.32.1.0/24. So we'll scan this subnet. It'll take a few seconds. Shouldn't take too long. This is going only through the most used and common ports. So we might miss some open ports, but it should find the most interesting usually. Okay, so we have a few open IPs. We won't go through all of them, but let's go through this one. We have 1032.1.10, and we have looks like HTTP port 8080. So let's look what we have there. We'll curl this IP 8080, and we are getting some HTTP response. and looks like it's actually REST API. And if we look through the HTTP response, we can see also the Swagger path. So we actually can get the whole documentation to all the possible paths that this service exposed. So let's go and get this JSON documentation, Swagger documentation. Okay, so it's to get a Swagger response, but to get let's 3D print it so we can really understand what it. Okay, so we'll 3D print it. So now we can get all the methods and paths of this path store service, this REST API service. So we have users, we have store orders, and we have some path. So let's try and get one of the paths here. So let's try to curl it. We saw there /path/ gets an ID. I'll go again to this path just to show that we really get it. /path/1 path ID. We can path delete. We can path get. So we'll just try to get to see if we have access to this. So we do have access. We get the first path in the service. So actually, right now we got. I'll go back to the architecture and I'll explain what we saw. So actually, right now we got access from one bridge front end pod service to actually almost the whole cluster. And I think so. Some of the ways to actually mitigate this with the ideas that Chaim talked before is to try and understand how we can narrow or minimize the blast radius, how we can minimize the attack blast radius that even from one bridge pod that might happen from like highly highly attacked pod like a front end service that an attacker won't get to the whole access to the whole cluster. So of course, one way is to just to use network policies and just disable the communication. So in that case, we actually can disable completely the communication between the front end and sensitive service, so they don't need to talk to each other. But more complicated scenarios usually appear in real time, in real world applications. And a cloud native application is that so we can't completely disable, for example, we can completely disable the communication between the front end and the Redis, right? Or the front end and the path store, because they have to communicate between them. But the other thing that we would like to minimize, for example, or to get visibility is to the application layer, to layer 7. For example, what commands are running, or what actually is going on between the front end and the Redis application, to try and, for example, see some anomalous behavior. Does someone, for example, starts running delete on all my database, or trying to extract all the keys, which is not a normal command that front-end application runs. Or for example, other use case for HTTP service is, for example, the path store. So the path store exposes a lot of paths, REST API calls, and also methods. So the front-end application actually doesn't have to use doesn't use all the REST API calls. It uses just some of them. And there are some more sensitive REST APIs that just the sensitive service uses. So in that case, we would like to apply some policies that the front-end application will be able to only to use some of the methods and some of the HTTP calls, but not all of them. And this is something that can be done in a layer 7 policy without actually putting the burden on the developer, which is always a good thing. So I think that's summarized some of the attack scenarios, some of the basic attack scenarios on a very simple cloud native application, and some of the mitigations when we get layer 7 visibility via visibility and via policy on layer 7. So Chaim, would you like to take it from here?
All right. So I would like to very briefly demonstrate what would a visibility dashboard look like when aggregating information from Envoy sidecars in a Kubernetes environment. We have here a Kubernetes cluster that we've deployed in AWS. It's running about 50 different deployments. We aggregated them to applications based on labels that are attached to those deployments. And we use the information we get from Envoy to build this map of service-to-service communication. So here we see our 9 applications, and we can zoom in into a specific application. This one is the HR application. It's built out of 5 microservices. We can see how many instances each one of them has, and we can drill one level deeper into a specific microservice, let's say HR travel. And we can see which instances it has. This one is a stateful set, so the pod names are actually meaningful. We can see which services access it, and not just which services, but actually which paths are being accessed, which HTTP methods are being used, and the same for outbound traffic. And once we defined access control, we can also start getting alerts of policy violations. So here we see the arrow, the red arrow between HR travel and finance invoices, which suggests that we don't have a whitelist rule that allows this traffic. And obviously, we can change the behavior to say whether we just want to get alert, or we actually want to block this traffic. And Envoy is very powerful in that sense. It not only provides us with a lot of information, it also provides us with the authorization primitives that are required to enforce an access control policy. And of course, we want to always be able to see our policy, which rules we define. Some could be service-to-service rules. Some could be based on different labels. Some could be ingress rules, identifying ingress IPs. Some could be egress rules, identifying possible domains. And again, Envoy is a great tool to help us actually implement those rules in our data plane. And of course, artifacts can be imported. The workload definitions can and should be imported from either Kubernetes or Istio, depending on what you have deployed. Obviously, if you're deploying Istio, Envoy is given. The mixer is already the natural point of getting all that information regarding traffic and policy. And then it's just a matter of connecting it to a dashboard to get that visibility, or just to build periodical reports. I think that's it for us. We'll be very happy to answer some questions at this point.
Thank you, Chaim, and thank you, Yevgeny. That was great. I think there were a few questions in chat that were answered. I think there's a couple that are still remaining. One question from Satish was, can the same principles be applied to legacy applications such as on-prem? I guess he's referring to non-containerized applications or VMs.
So I think you have to at least be able to extend the same principles to communication between your new cloud native application and your legacy applications. So even if you have your security controls already in place for your legacy applications, they will not be as effective when you need to start allowing access for microservices to your databases, your ERP, or any other legacy system. And so the principle is the same. The proxy and the sidecar approach actually works very well on VMs or bare metal, as long as you make sure that traffic is routed through the proxy. It can have exactly the same functionality. Some things are actually much easier in legacy environments, like identity bootstrapping, and actually attestation of identity is a lot easier in legacy system.
Thank you. A question from Farzad. Any difference in security for stateful versus stateless containers?
Not really. I think the nice thing about Kubernetes is that it has a very similar approach to handling both. So we have the concept of a pod, and in the cloud native approach, even if a pod is stateful, we still expect it to be able to go down sometimes. We have redundancy in place. We have locality of state. So the same principles in terms of the outbound traffic for a stateful container apply the same way as they do for stateless containers.
Thank you. A question from Jose. What types of security issues would an app face once service mesh like Istio is implemented? Or maybe you could compare and contrast what you did with Istio.
So we don't see ourselves as a competition or a different implementation. What we've been working on actually works really well with Istio. So as I mentioned, if you have Istio deployed, we don't do anything in the data plane, and we integrate with Istio's control plane to create all you need in terms of visibility and policy management. For users who haven't decided to use Istio yet, again, our solution is similar in the way we approach security. It's a little, we don't handle all the routing aspects that Istio handles. So that's the user can still configure their envoys for routing purposes any way they choose. Our focus is on the secure deployment of Envoy and getting the right identity to the right services, and handling access control and visibility. Anything else?
Question from Power Howard Zhang. Is it possible to have TLS for proxying to backend services? I guess he may mean backend non-containerized services.
Yes. So and that's a question that has been fundamental in Istio as well. TLS for egress traffic. So obviously, as long as we have the trust chain, so we can have access to the root of trust for those backend services, then there is no problem in defining a routing rule that says that egress traffic to a specific domain should be encrypted. And then it's just a matter of adding a client certificate, which can be very helpful for some of the backend services to identify the principal, the client that is contacting them.
A question from Adil. Do Istio and Envoy support SPIFFE?
So Istio does not use SPIFFE. They have their own way of managing certificates and attestations. Envoy, of course, works great with SPIFFE. Actually, all the certificates, the format, the SVID format for identity in the certificate is used in Istio and is natively supported in Envoy. So yes, Envoy works great with SPIFFE.
Thanks, Haim, and thanks, Yevgeny. Any more questions from the audience? There's a question from RT. Who are the vendors offering these solutions, and how do you see them differentiating from each other?
So cloud native solutions, there are a few in addition to obviously to Octaren. Some of them focus more on layer 3. Some of them are, their solution is more in layer 4. I think our solution from the beginning was focused on layer 7. And in that sense, I think we're thinking our way of thinking is very similar to what Istio has implemented. And I believe that is the right way to go, and I think that's where this whole ecosystem is going to, focusing on layer 7, having deep insight into the actual payloads and not just network identities.
Adil had a follow-up question. He read somewhere that Istio authorization is an implementation of SPIFFE. Is that correct?
So SPIFFE is not used for authorization. It's a way to distribute identities that can later be used for authentication. And on top of authentication, you can build authorization. Istio authorization is actually now just configuring Envoy's authorization based on identities. Those identities are, as I said, they're SVID, which is the format that SPIFFE promotes for identity. But if you're looking at kind of Spire, which is the reference implementation of SPIFFE, that one is not used in Istio.
Yeah, I think his question was, in fact, about authentication, not authorization. I misread his question. He just said auth. So is Istio authentication related to SPIFFE?
Yes. So as I said, the format in the subject alternative name in the certificate is the SVID format, which is specified as part of the SPIFFE specification, but the methods for attestation are not exactly what SPIFFE describes.
So we have time for just one or two more questions. Please put your questions in the chat window. And if there are no more questions, we'll close here. Thanks very much, Chaim. Thanks very much, Evgeny. That was very interesting, and I'm sure there's more to come on this important topic. We look forward to seeing you on a future CNCF webinar. The links and the recording will be posted. And have a good day. Thanks for joining. Bye.
Thank you.
Thank you.